Hey guys, welcome to day two. I hope day one went okay for you. I know there's probably a lot of different bumps in the road to manage, but hope you don't feel any stress about that. Just one day at a time, and we'll figure it out. Some of the bumps in the road were probably caused by me, and I apologize if that's true. I wanted to clear up one of the questions that was presented through Teams, talking about the group projects that you guys had been working on. The truth is, yes, I do want you to turn them in because I want to be able to give you some credit for having done it. So my intention is kind of twofold here. One is on Friday, I will not be giving you any new material at all. And the idea will just be that you guys will work on your projects, whatever needs to happen on that day. Kind of together, you can spend the 20 minutes that you would normally give to this class, you could give it to kind of clearing up and finishing up any of the last pieces of that puzzle. And then on Monday, I'll ask one of your group members, and if you worked by yourself, I'll ask you to send it to me. And that way I can kind of look through them and grade them and give you guys credit for the good work that you've done. And we do want to keep those in the back of our mind because a lot of what we're doing right now, talking about the Enlightenment and, of course, the other aspects like the scientific revolution and so forth, that's going to feed into what happens with the American colonies and their eventual revolution, the American Revolution. So those are things that we still want to be traveling with and thinking about, the American colonies, but it's going to be a couple of days before we see how the two things connect. For us today, we're talking scientific revolution. I mentioned just yesterday in the notes and briefly otherwise that revolution's a little bit of a strong term here. We want to maintain the understanding that science had already been happening. The revolutionary part of it is the fundamental shifts that took place. Philosophers of science call this a paradigm shift, a shift in understanding how something functions, how the universe functions. And so what we're going to be seeing today is that there are going to be some pretty significant shifts. One big shift is going to be in how our solar system fits together. And another big shift is going to be in how the body works. And these shifts are, in fact, revolutionary. Philosopher of science Thomas Kuhn, who's a really prominent thinker in the mid-20th century in regards to the philosophy of science, calls this paradigm shift revolutionary science. And so we are going to see some examples of revolutionary science, even though it's not the first time that science was being done. Anyway, let's jump in and just talk about a few different little things that are true of this era. Remember, we're kind of looking at like 1500 to 1750 here with all kinds of new insight to what's really actually true of our universe and our world and how even human beings function. So first things first, we have this old paradigm. Now I know you can't see quite all the slide here, so remember I have added the PowerPoint into the files at the top of our Teams page. You can access the entire PowerPoint or the notes otherwise. So if you can't see it here, don't get too upset because you'll be able to find it elsewhere. But the Ptolemaic system is one of the old paradigms that is going to break apart during this scientific revolution. Now, Ptolemy was a Greek mathematician, and of course, he's going to be doing some thinking in terms of astronomy as well. And Ptolemy is not alone in this endeavor in the ancient Greek world. Even Aristotle is going to contribute to this overall understanding of how the universe and the solar system fits together. But the thing is, they were both flat out wrong about how the universe and solar system fits together. They had what's called a geocentric view. And the Ptolemaic system is geocentric. What that means is it puts the Earth at the center. And this is something that many Christians readily accepted because they thought that it was affirmed in Scripture. They thought passages about the sun rising and the sun setting, and even the passage about Joshua making the sun stand still in the sky as he fought a battle. They thought all of that fit perfectly within Ptolemy's system, and so they were happy to embrace the Ptolemaic system, which of course will be an uncomfortable thing for them as they have to shift away from it. Now, the Ptolemaic system basically theorizes a few things. One, Earth at the center. Another one is that all the heavenly bodies that we can observe are essentially orbs of light that are embedded in these crystalline spheres that move in concentric circles around the Earth. And so the theory from Ptolemy is that, okay, the moon is in the first sphere, and then you've got Mercury and Venus, and then the sun, and you have these concentric spheres, and there are 10 of them, and he theorized that the 10th is what he called the prime mover. The idea was that this sphere moves on its own, and it gives movement to all the other spheres as it moves. And God resides beyond all that. God is beyond these concentric spheres. Now, what begins to happen with new technology and new, mathematical systems and tools to utilize is people test the Ptolemaic system and find that it's seriously faulty. Two of the most important people who are going to be doing this testing are going to be Nicholas Copernicus and, of course, Johannes Kepler. Now, Copernicus was Polish, and he's going to be doing a lot of this work in breaking apart the old paradigm and shifting towards a new paradigm, a paradigm shift, a revolution. And his paradigm will be towards a heliocentric view of the solar system, meaning the sun will be at the center of the solar system. And he actually has a lot of insight into how the solar system really functions. He surmised that the Earth rotates on its axis. And he writes all of this in his book On the Revolutions of the Heavenly Spheres, which you can see here on the slide, was published in 1543. And it really kind of opens a door, because a lot of mathematicians and astronomers that come after him are going to be confirming aspects of his work, like Johannes Kepler. Kepler's German, and as a mathematician, he's going to use observation and astronomical data to actually conclude and demonstrate that the planets don't have perfectly circular orbits like Copernicus thought, but rather they're elliptical, kind of egg-shaped. And so this was a little bit of a blow to people's sensibilities about what might look like a perfect solar system. They thought perfectly round would be perfect. Elliptical kind of seemed out of place for them, but Kepler was able to use math and observation to demonstrate that he was correct about his belief in the elliptical nature of these orbits around the sun. Their work will then, of course, be corroborated and confirmed later by Galileo. Now, Galileo ends up kind of being center stage for this conversation because of the way it brought him into some conflict with the Italian church. And that's something I want to address a little bit more directly tomorrow, because there are a lot of misunderstandings about how that worked. But he does make some observations through his telescope, an instrument that he sort of perfects, that were really, really helpful to establishing the heliocentric view as the correct one. For instance, he saw mountains on the moon. Now, a moon having mountains, it means it can't be an orb of light. It means it must be sort of like Earth, in that it's made of material. He also saw moons revolving around Jupiter. And that again establishes this idea that Jupiter can't just be an orb of light. He also actually observed sunspots, and really what he ends up being able to confirm is this heliocentric model. Now, we'll talk about how that played out for him in some of his conversations in public life tomorrow, but it's at least worth noting that he's a part of this movement, this paradigm shift. So is Sir Isaac Newton. Now, Newton, it should be noted, just like the three we've already talked about, was a devout Christian. Galileo was a devout Christian. Copernicus, Kepler, they were all devout Christians. And for Newton, he's going to be really feeling like getting to know the universe is helpful in his devotional posture towards the God of the universe, much like the others thought. And he writes his observations and his theories in his most prominent work, which is called The Mathematical Principles of Natural Philosophy, or sometimes called Principia Mathematica. And basically, this is where he kind of asserts the idea that gravity is central to all of this, to all this movement that can be observed. And he starts to kind of look at the universe like it's a machine that's working and functioning almost perfectly. That God is a great designer, and he put a design in place that functions well and is governed by law that was written by God, the law of gravity. And of course, these things start to really kind of confirm what Copernicus had laid the groundwork for. Now, it's not just in this Ptolemaic system and paradigm shift that we see revolution. We also saw or can see revolution during this time period in understanding of science of the human anatomy. For many, many centuries, the basic theories on how the human body worked went back to a Greek named Galen, and he had all kinds of crazy ideas about how the body worked and incorrect ideas. And these ideas will be shifted, and there will be, in a sense, revolution in this understanding by a guy named Andreas Vesalius. He's going to do dissections of the human body at the University of Padua, which is in Italy, and he's going to actually replace Galen's model of anatomy because Galen had been using animal dissections to come to his conclusions. There's also an Englishman named William Harvey who's going to establish that the heart is the center of the circulatory system. It's where the blood flows from and returns to, rather than, as Galen had assumed, the liver. And so these are obviously fundamental changes, and they're going to be important and helpful in starting to make progress in medicine, coming to understand how to support the human anatomy as it functions. One more area of breakthrough that we can point to in this topic in this time period is that in chemistry, and two very famous names that are worth mentioning. One is Robert Boyle. I'm sure you've heard of Boyle's law. Just nod your head and say you have. Your chemistry teachers will thank you. But basically, remember, the Boyle's law comes down to this idea that the volume of a gas varies with the amount of pressure that's applied to it. And so he's going to give us some breakthroughs in chemistry. But a man that's often called the father of modern chemistry is this man, Antoine Lavoisier. And he's going to actually give us a way of naming elements and sort of ordering them. And he does enough work that he gets this title of being the father of modern chemistry. And so as you start to add all this together, you start to realize, okay, the way they're observing, the application of reason, the utilization of new technology, all of this is bringing them into a new space of success in understanding how our universe works. And this is going to be fairly inspirational for philosophers, as they're going to say, wait, maybe the same sort of thing works in the humanities. If there's a law that governs chemistry and a law that governs physics and a law that governs the solar system, maybe there's law that governs the economy. Maybe there's law that governs the judicial system. And if we can just think deeply about what those laws might be, we can apply them and maybe come to perfect society. And they had a lot of optimism about how they might be able to do that. I wonder if you could start to think about how that optimism leads towards revolution. American and French Revolution, the optimism that they can change things for the better if they can just apply natural reason. And some of that optimism is coming straight out of these scientific advancements that we've been talking about today.